This is Unit 16, Acids and Bases, Part 2 Notes. By the end of this unit, you should be able to define pH and use the hydrogen or hydroxide ion concentrations to calculate the pH of a solution. Acid strength is relative to its concentration of hydrogen ions, or the H+. This can be mathematically expressed in terms of pH values. pH is defined as the logarithmic scale which expresses acids and base strengths relative to their hydrogen ion concentration. So the pH is based on the H+ ions that are within the solution. We use the formula where pH is equal to the negative log of the hydrogen ion concentration. If you see brackets, that stands for molarity or your concentration. The pOH is the logarithmic scale that expresses base and acid strengths relative to their hydroxide ion concentration. So the pOH is based on the OH ion, so you got to keep those straight. And again, the brackets are going to relate to molarity, so if you see the capitalized M, you're talking about the concentration of those ions. The pH scale ranges from 0 to 14. Strong acids are going to have a very high concentrations of hydrogens, and that refers to or relates to a low pH. Strong bases have a very low hydrogen ion concentration, and they will have a high pH. So if you have your pH scale here, bases will be at the 14 range, or between 7 and 14. Bases will be between 0 and 7. So we have the two separate areas, and the pOH is the inverse. The pOH is based on the hydroxide concentration, so acids would have very low hydroxides, hence a very high pOH range, and then the bases are going to have a very high hydroxide concentration, so they're going to have a low pOH. But we always need to refer to the pH scale because we can relate pH and pOH through the following equation on the bottom, where pH plus pOH is equal to 14. And if you compare it to the diagram at the top here, we have pH and pOH numbers, and if you add them across, they should always add up to 14. 8 plus 6 is 14, 9 plus 5 is 14, 0 plus 14 is 14. So if you ever have to compare a basic solution based on a hydroxide ion concentration, we always just calculate pH by subtracting it from 14. So the higher pH values are going to correspond to low pOH values. So again, bases have a very high pH, acids have a very low pH, and then the pOH scale is the opposite. But always refer to the pH scale to classify it as an acid or a base. Water is extremely important within the acid-base chemistry because it's amphoteric. That means it can act as either an acid or a base. So then whenever water ionizes, it can produce both H+ ions and then hydroxide ions, because H and OH together, that causes the solution to be neutral. So water has equal concentrations of H+ and OH-, so then we can relate those concentrations, which is of 7, to the hydrogen and hydroxide concentrations of 1.0 times 10 to the negative 7th. So using the last equation here, where Kw is the ionization constant of water, is equal to 1.0 times 10 to the negative 7 times 1.0 times 10 to the negative 7. Whenever you multiply the same base, you just add the exponents. So Kw of water is equal to 1 times 10 to the negative 14th. So both the hydroxide and hydrogen ion concentrations should both be relating to this Kw. So if one increases, the other one should decrease. And we can use any of the 4 previous equations or formulas to calculate the different values of our acid-base chemistry. So we have to be able to know if we're given pH, pOH, if we're looking for hydroxides or hydrogen ions, but there are multiple ways that we can calculate the acidity of any of these solutions. So type of example problems that you'll see are listed in the following. The first one is asking for the pH of a solution that has a hydrogen ion concentration. Our hydrogen ion is an H+, with the brackets around it, and that's going to directly relate to the concentration or molarity. And would this solution be classified as acidic, basic, or neutral? Well, if I'm given the hydrogen ion concentration, I can directly plug it into the pH equation, where pH is equal to the negative log of the hydrogen ion concentration. In this case, it's 1.0 times 10 to the negative 4th. Plugging that into the calculator, you'll get 4.0. It's less than 7, So the solution would be acidic. The next type of question is whenever they give you the solution in hydroxide ion concentrations. So we would have to use the pOH equation first to figure out the pOH, and then use the pOH to calculate the pH. So our negative log of the hydroxide ion concentration would be 2.20 times 10 to the negative fourth. Should be a 4. That's going to equal to 3.66. So that's our pOH. And then we can use another equation at the top to help us calculate pH based on pOH. Well, if they both add up to 14, if we wanted to calculate pH by itself, it would just be 14 minus 3.66, or 14 minus pOH. So then the pH would be 10.34, that's greater than 7, so the solution would be basic. So you have to be aware whether you're given the hydrogen ion concentration or the hydroxide ion concentration. Another type of question is whenever they're asking for the pOH of a solution with a hydroxide ion concentration of 1.0 times 10 to the negative 9. So the hydroxide you need to associate with the OH minus ion, and then we can directly plug it into this equation to calculate pOH, which is 1.0 times 10 to the negative 9. That's going to equal 9.0. That's your pOH. If you want to figure out whether it's acidic, basic, or neutral, you have to subtract pOH from the 14. That gives you a 5 pH value. That's less than 7. So ideally that solution would be acidic. And then the last type of question is a little bit different because it gives you the compound, the compound that they dissolve in solution. And they're asking you to find the pH of a potassium hydroxide solution with a concentration of 2.20 times 10 to the negative 4. Well, we have to understand that KOH is a strong metal. It's going to dissociate completely into K plus and OH minus ions. So this concentration is going to directly relate to the hydroxide ion concentration. That way we can directly plug it into the pOH calculation. So we have negative log of 2.20 times 10 to the negative fourth. That's again going to equal 3.66. To get pH, we just take 14 minus 3.66, and that'll equal 10.34 pH. And I know we've seen this problem or this number back in the second example, but I'm just showing you the different way that they could ask it. So you have to understand if this compound will dissociate into hydrogen ions or hydroxide ions. Alright, so have you accomplished the objectives? If not, please go back to the beginning and rewatch the video, or take notes or write down questions that you may have whenever we go over this in class.